Welcome to our presentation on Plinian eruptions in Chilean geology. We are
Eva,
Matt,
Agnes, and Brian.
First, we will give you a quick overview of Chile's tectonic setting. Then we'll go in depth about Plinian volcanoes before showing you some interesting sites and structures we saw in Santiago and Villarrica.
Chile sits at the boundary of the Nazca Plate, the South American Plate, and the Antarctic Plate. On the western edge of Chile, the Nazca Plate subducts beneath the South American Plate, injecting volatiles and melting mantle rocks, causing a 1,400-kilometer-long volcanic arc in the Andes. See the map of the 4 volcanically active zones of the Andes: northern, southern, central, and austral, and a more zoomed-in map of the southern volcanic zone of the Andes volcanic arc.
The magma compositions are controlled by the extent of hydration of that subducted slab. So in the region we visited, andesitic, dacitic, and rhyodicitic magmas predominate. Eruption types in the zone encompass the full range of Hawaiian, Strombolian, subplinian, Plinian, and Vulcanian types. Plinian eruptions are the most explosive type of eruption of magma, and they produce tall, sustained ash columns with plume heights reaching over 25 kilometers.
Although we didn't see any Plinian volcanoes during our visit, Chile does have volcanoes that have had Plinian eruptions, including Cordon Cale, a volcano further south of Villarrica, which had a Plinian eruption in 2011 to 2012. Other notable Plinian eruptions in the world include the 79 AD eruption of Mount Vesuvius and Mount St. Helens in 1980.
Plinian eruptions have a silica-rich composition, so that lavas produced are rich in volatiles and are usually acidic to rhyolitic. The explosive nature of Plinian eruptions is due to the buildup and subsequent shattering release of pressure caused by exsolution of magmatic volatiles as volcanic gases accumulate and expand explosively below a plug in the volcano's vent formed by magma's high viscosity. The resulting eruption typically lasts hours to days, with millions to billions of kilograms per second of ejecta traveling at speeds of several hundred meters per second, causing tephra fallout and extending ash plumes into the stratosphere.
Villarrica, located in central Chile, consists of a 2-kilometer-wide caldera that formed about 3,500 years ago, located at the base of the presently active cone. During our trip, Villarrica was under a yellow alert due to the emission of volcanic gases, including carbon dioxide, sulfur dioxide, and hydrogen chloride.
Eruptions eject large amounts of volcanic debris, often resulting in pyroclastic features. Throughout our trip, we saw pyroclastic features such as pyroclastic density currents, lahar mud flows of pyroclastic material, and full deposits from ballistics ejected during volcanism.
Pyroclastic flows consist of rock fragments produced and ejected by volcanic eruptions, and the pyroclastic density current is dependent on the superheated gas and eruptive materials. Ignimbrites are volcanic rocks that consist of hard and tough and are pyroclastic flow deposits such as lepidolite, pumice, and volcanic ash. Lahars are volcanic landslides mixed with water and are less associated with pyroclastic flow. We visited one major lahar formed following the 1971 eruption. Surges and reductions in the flow velocity created layers of different class sizes. To compare ignimbrites and lahars, lahars have more sand, whereas ignimbrites have more ash. Bombs are also more common in ignimbrites.
Pyroclastic fall deposits form during explosive eruptions by the sedimentation of pyroclasts from an eruption jet and/or plume. Around Villarrica, these ballistics contain mainly lapilli and small tephra bombs of dacitic, almost rhyolitic composition.
On our journey up the volcano, we observed numerous volcanic structures. Here you may see many, including lava tubes, which allow flows to travel further without solidifying, because the outer layer of lava flow solidifies, while the interior of the lava flow flows away.
Below the volcano, we observed the lava flow fronts of 2 eruptive cycles. We also observed contact metamorphism from when lava filled the paleotopography eroded from the Pucon ignimbrite, oxidizing the top layers to the color red.
Textures was observed throughout all the lava flows. A'as are lava flows with low viscosity, whereas pahoehoes are lava flows with high viscosity. This is the result of silica and gas content, in which a high degree of both results in high viscosity. We observed magnificent lava tubes in these areas of pahoehoe flows associated with the side vent.
We hope you enjoyed our presentation about Chile. We hope you loved it. Hasta la próxima, Chile.